All right, welcome back to another calculus lecture. So this will be the penultimate lecture of the semester. And with this lecture and the next lecture after this, what I want to do is just take some time to show you some of the geometric problems that you can actually tackle fairly easily using some of the ideas in calculus. So what we're going to talk about today are volumes by cross sections, and I'll explain what that is in a moment. But maybe to motivate this, let me ask us some questions. So question, how do we compute area, volume? I mean, technically you could say hypervolume as well. We can go in higher dimensions, but area and volume, really just the same thing, but a different number of dimensions. 2 dimensions for area, 3 dimensions for volume. But how do we compute these things in general? We have some fairly easy examples, so we know how to do this for... Well, we can compute the area of rectangles, circles, cubes, prisms, well, rectangular prisms, so like boxes, etc. So this is fairly straightforward to do if we have something similar, like something simple like this. Maybe a few that are less obvious. How do we compute the volume of a cone or pyramid? So for those of you that had a very good elementary or middle school education, you might know the volume, the formulas for the volume of a cone or a pyramid, a square pyramid. I certainly don't off the top of my head. It's not something I have occasion to ever use. But, if I did need to know the volume of a pyramid, the Egyptians certainly knew how to compute this. How do I actually derive that? How do I go about doing that? So you can sit down and work it out geometrically and use some nice ideas just doing, drawing pictures and working out some things that way. But it turns out that to compute these two things in quantities similar to these, or volumes of objects similar to these, calculus really actually helps us, and in particular integration really helps us. So the pyramid is one we'll do today, and then the volume of a cone is one we'll come back to and revisit tomorrow. But let's just do a quick example of the method that we're going to use. I'll try and illustrate what we're going to do in order to actually compute these volumes. And actually we're going to compute some more general volumes besides these. But example, compute the volume of a cylinder of radius r and height h. So we certainly know we should get, well, the volume of a cylinder is pi r squared, the area of the circle, and then you multiply it by the height, so pi r squared h. So we know we should get pi r squared times h. But, if I didn't know this beforehand, how would I actually figure it out? Well, we know the area of the circle is pi r squared. And if we think about what the integral does, we can sort of think about taking our cylinder. So here I've got my big cylinder. So this is r, and this is h. I can think about taking this cylinder and sort of cutting it up into a bunch of little discs. And then what I can do is sort of add all those disks together. And this is precisely the operation that we've already seen with the integral. We sort of slice things up into tiny and tiny pieces, tinier and tinier pieces. That's how we do the area underneath a graph. We take our interval shorter and shorter, so until they're of infinitesimal width. So really what we can do is we can take a circular cross-section of the cylinder, compute its area, which we have already, and then we can integrate as h goes from, or as some variable goes from 0 to h, we can integrate over the length of the cylinder. So the volume then is going to be, we're going to integrate from 0 to h, so the length of my cylinder, or the height of my cylinder, not exactly a height as I've drawn it, but you get the point. Now I need to put in the area of a cross section, so pi r squared, and then I need to integrate with respect to some variable which is moving along this axis. So we'll just say x is sort of, maybe I'm integrating from left to right, and x is moving along this whole cylinder. So this volume then is the integral from 0 to h of pi r squared dx. Well, it's easy enough. This is just pi r squared. That's a number. Those are just fixed constants. The integral from 0 to h dx. And then we apply the fundamental theorem of calculus. What is the antiderivative of dx? Well, it's just x. Or the antiderivative of 1, it's just x. So this is pi r squared times x evaluated from 0 to h. And this is going to be pi r squared times h minus 0, which is just pi r squared h. And we get what we were hoping for. Okay, so in general, we can compute volumes by integrals of the form. Typically it'll be something that looks like this. So volume is equal to an integral from, 0 to some upper bound, u. So we're going to integrate some variable, and it's going to be area of a cross section at x dx. So the area of a cross-section here, it happened to be constant. The area of that cross-section never changed. But as we consider more general objects, that area may depend on the particular x value that I'm at. And so the area of the cross-section at x, I can integrate that over some range, 0 to u. It might be h in this case, might be 12 if we're looking at a particular problem. Could be, whatever we want. But we can compute this volume by integrating these cross sections. And again, it's sort of relying on this idea that the integral sees things as you chop them up into infinitesimally small pieces, here infinitesimally thin pieces, and then you sort of add those up. You assemble all of those pieces back together, and you get some final answer. And that's precisely what we're doing when we're integrating these cross sections. We're sort of adding up all these cross sections, and then when we integrate, we sort of move up a dimension. So if I integrate two-dimensional cross sections, I'm going to get a three-dimensional volume out. Okay, so let's go ahead and move on to this square pyramid problem that we were interested in. I'm going to pull up some notes because I don't want to mess myself up. Okay, so, example. So you can see some diagrams of this in notes 25 in the notes section, but that's what I'm looking at here. So by integrating the areas of horizontal cross sections, That is, if I took a square pyramid and sliced it horizontally through the middle, I want to know what that cross-section looks like. Derive a formula, formuoli, as it were, for the volume V of a pyramid with height h, whose base is a square of side length s. Okay, so if I wanted to sort of make a picture of what this might look like, here's my square base. Wow, that's bad. And then my pyramid might look something like this. Okay, so the height here would be h, and then this would be my side length s. The perspective here is very poor, but anyways, you get the idea of the object we're trying to understand. Okay, so I want to integrate the areas of a horizontal cross-section. So when I think of a horizontal cross-section, I am thinking of one of these squares that I would get if I cut the pyramid sort of halfway up as I'm moving from the base to the tip of the pyramid. If I cut it horizontally, what would the cross-section look like? It's going to be a square, so I need to know the side length of that square, and then from that side length I can compute the area. Well, it's not immediately obvious how to do that, but we can think geometrically in terms of similar triangles. So let me draw a diagram here that will hopefully help. So here, this is the sort of, if I cut the pyramid down the middle of it from top to bottom, this is what it would look like. This is a vertical cross-section going through the middle of the pyramid. So I have its height is h, and then length down here is s. And then what I'm interested in is actually this distance, as if I'm at the y coordinate. And what we're actually going to do is we're going to integrate from top to bottom instead of from bottom to top. It's a little bit more computationally convenient to think about it this way, as the distance from the tip to some point being your variable y, rather than from the base to some midpoint being the variable y. But if I think about this distance, and again, we'll just call that y, then this length, L of y, is this thing that I'm interested in. I need to know this in order to compute the area of this square, and then I'm going to integrate that square from top to bottom to get the total volume. Okay, well, how do I compute this L of y, with respect to S and H? Well, I have a pair of similar triangles here. Similar triangles being triangles where all the angles are the same. The side lengths might differ, but the angles are all the same. So the law of similar triangles says that the ratio of L of y to y is the same as the ratio of S to H. So this says that L of y divided by y, so if I take the side length and divide it by the height, that is going to be equal to the side length, the bigger side length S, divided by the height H. And so this gives me L of y as a function of y. And so L of y is equal to, well, just multiply y over y times S over H. And so if I think about the area of the cross-section at the coordinate y, or y units from the tip of the pyramid, the area of a cross-section is then A of y, we'll call it that, which is L of y squared. So the side length here, I have to square that in order to get my area. And then I just write down what that is. That's y squared times s over h squared. Okay? So if I think about being y units away from the tip as I've moved down by y units, then the area of the horizontal cross-section at that point, that square, is going to be y squared times s over h squared. So the volume then, well, let's just perform the integration. So this is equal to the integral from 0 to h. So I'm going to start at the top and then move h units down. I'm going to integrate my area function and with respect to y. Okay, that's all we're doing. And this is exactly the form of the integral that I wrote on the previous page. Some area function integrating along some interval. Okay? Well, let's just write down what this is. This is the integral from 0 to h of y squared times s over h squared dy. And then s over h, this is just a constant, so it comes outside of the integral. So this is s over h squared times the integral from 0 to h of y squared dy. And now we just apply the power rule. This is a nice easy integral to compute. So we have s over h squared times y to the 1/3. I'm sorry, not y to the 1/3, y to the third. And then there's a 1/3 that comes out from the power rule. So I added 1 to my exponent, and then I divided by my new exponent, which is 3. And then I evaluate this on 0 to h. The 0 term doesn't matter. When I evaluate it at 0, it comes out to 0. So really, this is just going to be 1/3 s over h squared times h cubed. And when you simplify, this gives you 1/3 s squared times h. And indeed, if you were to go look that up, this is precisely the volume of a square pyramid with side length s and height equal to h. Interestingly, this sort of bears a resemblance to the triangle, the area of a triangle. So, remark, the area of a triangle is 1/2. If my base is s, it would be like 1/2 base times height. So, you know, I have a 1/3 here instead of 1/2, so it's sort of indicating the number of dimensions, perhaps. And then I have an s squared for the area of the square rather than just the side length. I've sort of moved up a dimension here. Anyway, something to think about, something to maybe explore. Okay, so that's the volume of a square pyramid. I expect you all to use this every day throughout the rest of your life. It's really important that you know this and you understand it, and it's very applicable in everyone's everyday life. So let's go to an even more esoteric problem, just to see that this method is quite robust in sort of the things that it can handle. If you couldn't detect my sarcasm before, I'm sorry. Okay, so I actually want another example here. So example, and this one's going to be more difficult to visualize, but we're still going to be able to compute the volume. So compute the volume of a solid whose base is the unit circle, x squared plus y squared equals 1, the set of points x and y that satisfy this equation, and whose vertical cross sections perpendicular to the x-axis, and we'll draw a picture here in a moment, are isosceles triangles, where the height is equal to the base. Okay, so what exactly is this object that I'm trying to compute the volume of? This is, I mean, what the hell are we looking at here? So let's maybe try and draw a picture. So here's my unit circle. And then what I have, so here's my x-axis, here's my y-axis. I have vertical cross sections perpendicular to the x-axis. And so what I mean by that are, you can imagine cross sections going this way, sort of coming out of the page. And coming out of the page are going to be these sort of triangular shapes. And I'm trying to add a little bit of perspective to the drawing here. But you can imagine triangles that are sort of sticking out of the page vertically, and the tip is precisely aligned on the x-axis, okay? And then that's going to sort of move, the top of it is going to move up and down as the base gets wider and then shorter again. So maybe to help visualize this, we can go into mathematics. So how do we go about doing this? Well, let's just go ahead and do the same process that we've done. So what is our area function? Is a of x. Here we'll make it depend on x because we're going to integrate along the x-axis. And also we need our limits of integration. Well, those are easy. It's just -1 to 1. It's the boundaries of the circle. So we need to think about what the area of one of these triangles is. Well, the area of a triangle is 1/2 the base times the height. We just wrote that down on the previous page. So what are the base and what are the height? Well, I've said the base and the height are equal in this problem, so it's a little bit more straightforward. So what is the base going to be here? Well, if I think about what this y value is, depending on x, I know that the top part of a semicircle is given by this. If I just solve this equation for y, I get y equals 1 minus x squared, and then on the bottom it's the same thing but just the negative. So these two functions, if you were to graph them individually, they give you the top half and the bottom half of a semicircle. So I can use that to compute the base of my triangle. So at x, the base is, well, this part of it from the axis up to the actual circle is precisely this quantity. But I have to go down the other way too, so it's going to be twice that quantity. So 2 times the square root of 1 minus x squared. Okay, so now let's go ahead and plug that into our area formula. So the area is a of x equals 1/2. The base and the height are the same, so I actually just square this quantity. And so the 2 squared becomes a 4, but then I divide by a 2, so this is going to be 2. And then the square root of 1 minus x squared quantity squared is just 1 minus x squared. Okay? And now all I need to do is integrate this area, the cross-sectional area, from -1 to 1. So the volume is the integral from -1 to 1 of a of x dx. And this is equal to negative 1 to 1. I pull my 2 out front of the integral. I have 1 minus x squared dx. Apply the power rule to each of these. This is going to be 2. 1 integrates to x, and then x squared is, or negative x squared is going to be negative 1/3 x cubed. And then we evaluate this from negative 1 to 1. This is equal to 2 times 1 minus 1/3. So I plug in 1 here, plug in 1 here. I get 1 minus 1/3. And then because this is an odd function and I plug in a negative 1 here, I'm actually just going to get the same thing. So I'd have a negative coming out from this negative in each of these odd terms, but that's going to cancel with the fact that I do a subtraction whenever I do the fundamental theorem of calculus. So all in all, we're going to get something like this. And this is 2 times 1 minus 1/3 is 2/3. So this is 4/3 because I have 2 of those here. And so I'm going to get a final answer of 8/3. And so even though this object is sort of rather abstract and somewhat difficult to conceptualize without the aid of computers, we can still do this process and compute its volume. And in fact, it's a fairly straightforward process of computing this area and then integrating that area. And that's really all we're doing here. So I think that's sort of a neat thing that calculus allows us to do. So in your homework, there's going to be another problem like this, but we're going to replace the triangles with squares. And if you want to see until then, I'll see you all in the next lecture, I guess.